So today is November 7th, and I did record the lesson in class, but there was a lot of downtime when students were working on something, and then we would come back and do the lesson. So I decided to just go ahead and record straight through. If you're watching this either to review or if you missed the day, you can pause it whenever I tell them to attempt like an activity, basically to attempt a proof. That's what we're doing, is still writing proofs. You can pause it and try to do what we did in class and then unpause it when you're done. And that'll make it a much shorter video. So just starting I didn't really use the notebook lesson a whole lot. Mostly we worked from the book, but we did have bell work. So let's talk about the bell work first. Again, you can pause it and try to do the bell work on your own. So this was the bell work. I said if point B is the midpoint of AC, so there's a visual down there. Sometimes you'll get a visual, sometimes you won't. I asked you to write two statements based on the fact that point B is the midpoint of AC. So I've talked about midpoints a lot. I emphasize that in class even more today. You have got to understand why you would be given midpoint information. I guess you need to understand when you are given midpoint information, what the conclusion is that you can draw, what reason basically you can use in a proof. So the only real unique statement you can make, so pause it and try to write the two statements, by the way. Pause it. You should be done, so now you're back. So there's really only one statement that you can make that is unique to the fact that that B is the midpoint. There's another statement that we'll make, but it's really not unique to point B being the midpoint. So the statement you can make, down a little bit, based on the fact that B is the midpoint. Here, I'm going to do this with my finger. Hopefully that's fine. There we go. We can say, okay, well, if B is the midpoint, that means we have divided the line segment in two. So if I put a midpoint, or approximately where the midpoint would be, that means AB is congruent to BC. That's really the only statement that you would be able to say is unique to the fact that B is the midpoint. Oh, we can also say from that statement, so that's the midpoint theorem because it's about congruence. We did a proof earlier. If you're not understanding what I'm saying, the very first lesson we did on writing proofs, there was a proof that talked about what's called the midpoint theorem. And it states that the two segments are equal, but really it states that they're congruent, which is what that symbol is right here in the middle. That's a congruent symbol. I didn't do a great job of drawing it, but you'll see it in the bookwork that we do in a minute. So that. Then there was a second statement that we could make that says this: AB equals BC. So we said this is called the definition of midpoint. And I'm going to abbreviate midpoint. So they're really saying the same thing. It's a very small technical difference. When we talk about the midpoint theorem and congruence, we're saying that this segment AB could fit right on top. We could lay it right on top of BC, and they would basically be the same line segment. AB is congruent to, or it's really the same line segment as BC. This down here is talking about the measure of the line segments. We're saying that the length of AB is equal to the length of BC. So small difference. I'm not really worried about that for our lessons, as long as you understand that if I tell you something is a midpoint, we're saying this segment has to equal this segment. So that's not the two statements. That's really, I'm considering that one statement. The second statement you could write, again, I asked for two statements. And tell you what, I'm going to move the line up a little bit, and we're going to do the other statement above the line. So this statement is really true in other situations as well, not just when it's the midpoint, but it's still true when B is the midpoint also. This statement would say, I guess I can, we'll write it. This statement that we learned a long time ago says that AB plus BC equals AC. And we could also make that into a congruence statement as well. I could say that those are the segments and that those segments are congruent. AB plus BC is congruent to AC. That's true whether B is the midpoint or not, as long as B is in between A and C. Again, if that's confusing to you, I'll show you what I mean. Let's say B wasn't there, but B was, let's say B was down here. Well, again, definitely not the midpoint, but AB plus BC is still equal to AC. Or if B was way down here, again, AB plus BC would still be equal to AC. So again, that statement has nothing to do with the midpoint, but it is still a true statement. It's still a statement that we could use when we are doing proofs, and we are going to use it today. That's one of the main theorems or postulates of today. And I'll tell you what the name is in a minute. It's called, well, it's called the segment addition, line segment addition postulate, I think it is. So let's go ahead now. We'll go into the book. Oh, wrong book. Oh, how do I do not get to our stuff? Oh, there we go. I don't even know how I did that. All right. So in the book, we were done with the first lesson writing proofs. Now we're on proving segment relationships. This is page 163 of the pages. This first number always matches up with your pages. So we said there's a ruler postulate. I don't plan on ever using that in any proofs. I am going to make up your quiz, by the way, if you weren't in class. I'm going to go ahead and create a quiz instead of using the book quiz. You'll see that the book reasoning, I think, is more complex than the reasoning that I'm going to use, that I want you to be familiar with. They use a lot of theorems and postulates and properties that you will probably never be able to recall. You may or may not even be able to pick them from a list. So I'm going to stick with some of the more basic ones that I think are the most important for you to know. Just know on a district test, they'll probably use some more complex stuff. Just do your best to pick the right one. So the ruler postulate simply says if I have a line segment, which they have down there, and they've assigned 0 to point A, that means there is some number associated with point B. And it's going to be a higher number than 0. It's kind of like a number line, basically. The points moving to the right are going to have higher values. So I'm going to draw a different, I can't draw a different line segment. Shoot. Tell you what, I'll go back over here. So here's what I think the ruler postulate means. If I have a line segment, that's not a line, there we go. If I have a line segment, again, I have 2 points, and then let's say I have a third point. If this number is 5, for instance, well, then the numbers on the right have to be higher numbers. So let's say this number is, I don't know, let's say 3. I'm sorry, 8. Well, if that number is 8, then the next number has to be higher, but not a lot higher, because that segment from 8 to 9, it's a much shorter segment than from 5 to 8. So there needs to be kind of like, it's not symmetry is not the right word, but the length of the segments kind of need to make sense with the numbers. So that's, to me, kind of what the ruler postulate means. Not really probably technically accurate, but that's kind of what I want you to think of it as. It would also mean, I guess you could say that if the length of that segment is 3, the length of that segment should be about 1. So again, there's kind of a ratio between the segments based on how they look. Although sometimes they are going to draw segments that maybe don't look the same length, but that are congruent. Although that really proves for sure. So. All right, so back to the book. So the next postulate is one that you definitely have to know. We will definitely be using that. It's kind of the whole point of today, and it's this postulate for the most part, segment addition. It says exactly what we just talked about in Bellwork. So the segment addition postulate, you have got to know this one, or you could call it line segment addition postulate. It is the one that says AB plus BC equals AC. So when we did this a while back, we said little plus little equals big. We did that for line segments and for angles, actually. So we can use that same concept. Little plus little is big, but the actual name of that postulate is segment addition postulate. That would be a reason you could use in a proof, because that is a proven postulate, a proven concept in math. If it's been proven, then we can use it in proofs. Then we went to the next page. I think there might have been a proof we did. Yeah. So, and I can't really zoom, or can I? I don't think yeah, I can only zoom in. I can't zoom out. So unfortunately, I have to scroll through this a little bit. So you should have your book pages out. This is page 164. If not, you can scroll or rewind or scroll back. Well, you can't really scroll, so you'd have to rewind. Here's the given information, and here's what we're going to prove, and here's the image. I'm going to scroll down, so that's not going to be on the screen anymore. But just kind of remember the given information is that Q to T, so from here to here, is congruent to RV, which is from here to here. So basically this line segment here is congruent to this line segment here. They want us to prove that this little segment is congruent to this little segment. And they look similar, but until you prove it, you can't say for sure that they're congruent. They're the same size. So we're going to prove it based on the given information. That I sure can. I already finished it in class. And oh. All right. So, and we actually are going to use different reasons than they use in the book. Again, I'm not concerned about you trying to remember everything you've ever learned in math. I want you to focus on some of the basic theorems and postulates and basically the reasons you could use in. So first we said this. I'm going to ask you this. You can pause it briefly if you want to try to answer it and think about it. How do we always start a proof? What is always going to be the first statement and the first reason? Pause it if you want to think about it. Now that you're back, the first statement is always what is given. It's not necessarily every given statement, but it's going to always be one of the given statements. In this particular proof, we only have one given statement, so it has to be this. And the first reason is always given. We have to start with something that is known, that we are given. From there, we are going to go step by step, and we are going to use one reason at a time to get to the next step. So kind of one, again, it's just step by step when you're doing a proof. You can't really jump from the beginning to the end. Now, another thing I said in class is if they give you one of the two columns, so this is a 2-column proof, by the way. If they give you the reason but not the statement, I think that's the easiest thing to fill out because they're basically telling you how you went from line 1 to line 2. They're telling you right here. Well, we use the definition of congruence. So, especially once you've seen enough proofs, you should be able to figure out, okay, I just used the definition of congruence to go from here to here, and then you should be able to certainly pick that from a dropdown. So I don't think those are super difficult. Next, if they give you the statement but not the reason, then you should hopefully kind of be able to figure out, okay, well, how did they get from step 2 to step 3? What's the reason that allowed me to go from here to here? Because again, you would already have filled this out. So you'd be able to see this, you'd see this, and hopefully you'd be able to then fill out what the reason is. They're telling you right here what they're stating. So you just have to come up with how they were able to state that. That's a little more difficult, but still, from a drop down especially, I think you should be able to pick that out. This is where it's the most difficult, when they don't give you the statement or the reason. You got to come up with both. That's going to be the tricky ones, and that would be like the highest level of achievement, like on a quiz. If you wanted to get a 4, if you wanted to get an A, basically, you would probably have to be able to come up with both of those. The other ones would certainly get you a passing grade, higher than a passing grade, even really. But to get an A, you're going to have to be able to come up with both reasons. All right. So let's go ahead and start filling it out. Again, we know the first one is given. It tells us definition of congruence. So I'll let you think about what that is. It's kind of similar to when we said the difference between midpoint theorem and definition of a midpoint. So you can pause it and think about it if you want to. Otherwise, I'm just going to give you the answer. So you should be back now if you paused it. So when we say definition of congruence, we're just taking this statement about congruence. I think I do have to do it in this little editor thing. And we're just saying, all right, well, if two things are congruent, try that again. There we go. If two things are congruent, that just means that their length is equal. So we would type in this. We would say QT equals RV. And this would work going the opposite way also, by the way. So if we were able somehow, or if we were given information that two things are equal to each other, the definition of congruence would state that they are congruent to each other as well. So you can go in both directions with that. So now this next one, I'll let you think about, well, how did I get from QT equals RV down to this? I will tell you this one's a little tricky. I'll give you a hint. They're not actually saying we're going from 2 to 3 in this case. In this case, they're kind of just stating this all by itself. And I want you to try to figure out why they can state that. If you need to look up at the picture, that might help. Look at really, you don't even need to look at the given information. That doesn't have anything to do with it. Look at the picture and try to figure out how are they able to state QR plus RT equals QT. So I'll give you a sec, and then it's really the same reason here, which is why there's only one box to fill out. How are they able to state RT plus TV equals RV? So pause it, try to figure that out. You should be back now. So again, this is a little tricky, but I expect you to know this one. I expect you to be able to tell me the reason for that, especially since, didn't notice, it's actually right at the top of the page, segment addition. This is that concept we just talked about in bell work. QR plus RT equals QT. That's the segment addition. Little plus little equals big. Then it's the same thing for RT, TV, RV. RT, this little segment, plus this little segment equals this whole bigger segment. That is the definition of the segment addition postulate. So we would say segment addition postulate. So that would be the reason that we can state this right here. Again, it's not how we got from this step to this step, which a lot of times it will be how we're going from one step to another one. In this case, we're just stating this based on the given information and really more the picture, frankly. All right. Now we need to try to figure out, all right, how do we get this particular statement and reason? Because we don't have either of them. What I said in class, a good strategy, and you might have no idea how to go from this right here to this down here. There's a lot of different directions you might be able to go. So what I suggested, what I would do is I would actually look at the next step and I would work backwards. If I'm going from step 4 to step 5, let's assume that that's what we're doing. We're going from 4 to 5, that this is not just it all by itself, some theorem or postulate, that they're just adding in like they did in line 3. Let's assume we're going from 4 to 5 in this case. When you go from one step to the next, you're making some kind of a change to the statement typically. So in this case, it tells us what the change is. That's the reason. It's telling us when we go from 4 to 5, we're using the subtraction property of equality. That's why we're able to go there. Well, here's the subtraction property of equality. So this is another one you do kind of need to be aware of. There's actually a subtraction property of equality, an addition, a multiplication, division. All it means is we are subtracting the same thing on both sides. That would be the subtraction property of equality. Well, if I'm subtracting, if this is the new thing that I'm adding to go from step 4 to step 5, this wasn't in step 4, subtract RT was not in step 4, but everything else would have been in step 4. The only change from step 4 to 5 is to subtract RT. So, and if you're not getting what I'm saying, that a lot of kids struggled with it. There were a few that got it, but I am saying that QR, oh, I got to click on this thing here. QR plus RT equals RT plus TV. That would have to be the line in 4. Because then I could say, okay, well, from this left side, which is right here, I'm going to subtract RT. From the right side, I'm also going to subtract RT. So that's kind of how that would look and how I worked backwards. If you look up at the step above, there's another way you might have been able to figure out where you needed to go with that. Although it's kind of hard to know what direction you're going. It's easy to tell the reason now that we've written this in, at least I hope it's easy. But if this was just what you were looking at and you were trying to get to this step, you might not necessarily know what to do if you're trying to go from 3 to 4. So again, working backwards will sometimes help. So what the reason is, and I emphasize this a lot in class, I'm not going to do it as much on the video. Substitution is going to be used in a whole bunch of proofs. Like it may not be used in every single proof, but it's going to be used in a lot of them. Especially anytime we have a bunch of equal signs. We said that. We got a congruent sign, we got an equal sign. Oh, congruent signs kind of are the same hint, just like an equal sign that substitution might get used. So now let's see if this would make sense to say I somehow use substitution to get from this line to this line, because I don't see any substitution as a reason yet. So there's a good chance this is substitution, but let me see if that makes sense. Well, I know up here that QT is congruent to RV, or I could say QT equals RV. So I could kind of substitute in some things maybe for QT or for RV. Well, down here, I know QT equals this, and I know RV equals this. So let's see, does that make sense? Well, if I substituted in this right here, QR plus RT, if I substitute that in for QT, that would make sense. That would give me this right here. I'm replacing QT with this right here because that's what QT equals. Okay, well, can I do the same thing for RV? Can I replace that with this RT plus TV? Well, yeah, look, right here it says RV equals RT plus TV. So again, if this RV equals this right here, and unfortunately I can't write on the screen like I did in class, but if you imagine there's a box around this right here can replace this RV because it says right here, that's what RV equals. So that's how I can replace that with RT plus TV. So yes, substitution makes sense. They actually use something different in the book, I believe. I'm fine with you using substitution in that case. Tell you what, I'm just going to show you the book and the way they did it. So they use the reflexive property, I think maybe on number 6 or something like that. But here, we'll go ahead and look at the book and I'll show you how. I told you before that I get to, oh, here. I told you before, if you gave a proof to 5 different math teachers, you might get 5 different proofs back and they might all be correct. So here is the proof we just did, I believe. Yeah. So again, substitution was our 4th. Oh, they did actually use substitution property again. So, oh, but I wouldn't have used substitution. I would have gone straight from this line here, and I would have just gone straight from QR plus RT to QR equals TV. And my reason would have been the subtraction property. Because I would say, well, I could subtract RT from both sides, and therefore I would be right here. So they showed it, and that's where they put subtraction property. But I would say the reason I can go from 4 to 6 is the subtraction property. I'm not sure why they're showing this step in here and physically writing it out. But either way, then they said substitution, which I'll be honest, I don't really get how they are calling this substitution going from here to here. To me, this is just math. RT subtract RT is 0. RT subtract RT is 0. I don't really get the substitution part of that. Just gonna be honest. You do need to understand, again, definition of congruence. So I went from an equal sign to a congruent sign. I changed QR to segment QR, TV to segment TV. So that is one you need to know, definition of congruence. So there are 3 important reasons, and well, given is always important, but definition of congruence, you need to understand that that just means that you're going from congruence to equals, basically. Substitution property, that just means if you have something that's equal to something else, then you can exchange those somewhere else in the proof. And you do need to understand, you need to understand what subtraction property of equality is. Also, that wasn't really the one I was thinking of, but you need to understand if you subtract the same thing from both sides to get rid of something, that's subtraction property. Same way with if you add something to both sides, or multiply on both sides, or divide on both sides. But you also need to understand the segment addition postulate, that the little segment plus the little segment equals the big segment. Little plus little is big, just like we did in segments before, and then we did it again really in angles. In angles, though, it'll have a different name. It won't be called segment addition. It'll probably be called angle addition postulate. So I don't want to show you that yet. So go ahead and try to do the proof at the bottom of the page on your own, and then we'll pause the video, try to do it. Us doing this in class, to be honest. Yeah, maybe skip to the next page already. So go ahead, try to do this on your own. I'll just do this one real quick, and then we'll get to the next one. Spending longer than I wanted to on this. Page 164. All right, so first reason, oh, so you should have unpaused it. First reason is always given. That's an easy one. So now, how do I go from this to this? Well, looks to me like we're keeping the same letters, and we just went from congruence to equals. So that's definition of congruence. Got to speed up because my battery's about to die. Now, and that is the case for both of these, definition of congruence. Now we got to figure some stuff out. CE plus ED equals CD. Well, if you look at the picture, or if you just understand how the order of these letters works, CE plus ED, little plus little equals big. So you should know that's the segment addition postulate. I expect you to know. Segment addition is all I'm going to write there. Now let's look at the FE plus EG. Well, FE plus EG equals FG. Again, same thing. I don't know why they wrote it on 2 different lines this time, but they didn't write it on different lines. For segment addition again. Now, if you'll notice, I still haven't used substitution, and I've got a bunch of equal sign and congruent signs. So I'm pretty sure substitution is going to be in here somewhere. So let's see, FE plus EG equals FG. Oh, wait, hold on. They're doing, I totally messed something up. They said FE plus EG is CD. So I was wrong. FE plus EG is CD. Let's see how we can get to that. It's actually not segment addition because that's the next one. Sometimes you got to back up and rethink it. So this is segment addition. We'll skip down to that. Because again, FE plus EG is FG. FE plus EG is FG. I didn't even finish reading this. I just started figuring something out. So FE plus EG is CD. Well, that's a little trickier than I thought. So this is the same here. Somehow is CD. CD. Boy, I don't see anything about CD anywhere. So FE plus EG. I'm going to think about this one myself for a second. Oh, okay, I got you. So they're doing here's substitution right here. It says CE is congruent to FE, so they replace CE with FE. ED is congruent to EG, so they replaced ED with EG. So new substitution was going to be in there somewhere. When in doubt, think about substitution. Substitution. So again, that's always a good go-to. So we just replace these two. Now that leads us to this. So this is segment addition postulate right here. Now we can kind of come back to substitution. If I know FE plus EG equals CD, then I can replace FE plus EG with CD. That comes from this line right here. So again, I'm doing substitution again. And then now this is definition of congruence. But I'm going to run out of battery. Not going to get, unfortunately, to the ones that I wanted, but that's fine. All right, let's see if we can finish these last two up real quick. 2 or before the long one. Oh, actually, those are just properties. I'm not going to waste any time on those. Their substitution basically is the one you need to know over those. All right, so quickly, you want to pause it and try to figure out 165, the proof at the bottom. I'm just going to move forward. So pause it now if you want. Midpoint. Anytime you see midpoint, you better be thinking that the two segments are equal. So in this line, the two segments will be equal. In this line, the two segments will be equal because T and R are midpoints. So they tell us that right here. So midpoint theorem. Now, this was just given. A lot of times you're going to have given information that hasn't been used in the beginning, and that should be a pretty easy one to fill out for a reason. This is not we didn't go from congruent to congruent, so it's not the definition of congruence. I would say if this doesn't change, all we're doing is replacing this. I got to go with the fact that that is going to be substitution. The book actually uses something different, I believe, but it says right here that right here, VT is congruent to TS. So we're just going to replace VT with TS. That's substitution to me. I think in the book it uses the reflexive property, which is this property up here. You can say if, symmetric property. If AB equals CD, then the opposite is true. Congruent. Then CD is congruent to AB. Transitive property would be if this equals this, and then if this equals something else, then the first thing and the third thing are also equal to each other. My battery's going to die. All right, so our last step, again, they use the symmetric property right there. This was, I think, in the book Not transitive property, but something else. Oh, actually, here, I'll show you real quick. So for this particular, so it was the, that's not the one. Next page. Yeah, there we go. So they use transitive property. They use that twice actually. So again, substitution works just as well for transitive property. That's why I didn't really spend any time on it. It's based on the substitution principle, this transitive property is. So it's just, I'm trying to prevent you from having to remember. So now remember, if you don't see substitution, but you do see this, there's a good chance that'll be your answer, transitive property. Let's try to finish. My batteries second, 16%. Oh, so this right here would be we'd actually be done in my book because we would have already gone. I would use substitution again because I would just replace QR. So QR equals RS. So I would just be replacing QR with RS. I'm not exactly sure why they didn't do it this way. QR equals TS because TS was already in there. You'd have to make it congruent though. You'd have to put the line segment above RS and TS and then use a congruent symbol. I just am in a hurry with my battery dying. So, and I'm not sure I know how to do that in that little equation editor. I can't write on the screen in this. So this was the last proof we did. I'm not going to have time to finish it. So I'm going to show you should be able to come up with reason 1 through 6 though. We did it in class. We did finish it in 7th period, I think barely, but I'm just going to show you the answer to it since I'm really super short on time. That's not it. So I think we got to go to the next page. Oh, how do I go to the next page? Oh, there we go. So here were the reasons. Try to do it on your own.